Section 1 and 6 is about the design of experiments. So we're going to have 5 different objectives for today. So first we're going to describe the characteristics of an experiment. Then we're going to explain the steps in designing an experiment. For 3, we're going to explain the completely randomized design. Then we'll explain the matched pairs design. And then we'll explain the randomized block design. So for our first objective, to describe the characteristics of an experiment is a controlled study conducted to determine the effect of varying one or more explanatory variables or factors has on a response variable. Any combination of the values of the factors is called a treatment. The experimental unit or subject is a person, object, or some other well-defined item upon which the treatment is applied. A control group serves as a baseline that can be used to compare to other treatments. And a placebo is a harmless medication such as a sugar tablet that looks, tastes, and smells just like the experimental medication. Blinding refers to non-disclosure of the treatment an experimental unit is receiving. In something called a single-blind experiment, that's one in which the experimental unit or the subject doesn't know which treatment he or she is receiving. So in general, you're either probably going to get the placebo or you're going to get the experimental drug. You just don't know which one. In a double-blind experiment, that's the one in which the experimental unit and the researcher in contact with that experimental unit don't know which treatment the experimental unit is receiving as well. You're going to see, because if you are doing a single blind study, the researcher can influence the opinion of your subject. Okay, again, sorry, the answers are already up, but we'll discuss. So for this example, the characteristics of an experiment, the English department of a community college is considering adopting an online version of a freshman English course. To compare the new online course to the traditional course, an English department faculty member randomly splits a section of her course. Half the students are going to receive the traditional course, and the other half is given an online version. At the end of the semester, both groups will be given a test to determine which performed better. So for part A, who are the experimental units? They're the students in the class. They're the ones that are going to either receive the online instruction or the in-person instruction. For part B, what is the population for which this study applies? All the students who actually enroll in that class. And what are your treatments? Your in-person education or your online instruction, or traditional versus online. And what is your response variable? How are you going to measure the success of this study? You're looking at your exam scores. Why can't this experiment be conducted with blinding? Either way, if you wanted to do a single blind study and you didn't want your students to know, kind of impossible, because they're obviously going to be in class or in front of a computer screen, so they'd know which one they're receiving. And same thing on the teacher aspect of it. You couldn't do a single blind from that side because, again, the teacher knows whether they're delivering an online instruction or an in-person instruction. If you can't do a single on either side, then you definitely can't do a double. So for objective number 2, we're going to explain the steps in designing an experiment. To design an experiment means to describe the overall plan in conducting the experiment. So the first thing that we want to do is identify the problem to be solved. It should be explicit, it should provide the experimenter direction, and it should identify the response variable and the population to be studied, and often we're going to refer to this as the claim. For step 2, we're going to determine the factors that affect the response variable. Once the factors are identified, it must be determined which factors are to be fixed at some predetermined level, the control, which factors will be manipulated, and which factors will be uncontrolled. And you'll see an example of all these in just a second. For step 3, we're going to determine the number of experimental units. And for step 4, we're going to determine the level of the predictor variables. So for number 1, the control, there are 2 ways to control the factors. First, you can fix their level at one predetermined value throughout the experiment. These are variables whose effect on the response variable is not of interest. Or B, you can set them at predetermined levels, and these factors whose effect on the response variable interest us. The combination of the levels of these factors represent the treatments in the experiment. And the second thing that we're going to do is randomize. We're going to randomize the experimental units to various treatment groups so that the effects of the variables whose level cannot be controlled is minimized. The idea is that randomization averages out the effect of uncontrolled predictor variables. Okay, and then for step 5, we're actually going to conduct the experiment. Okay. Part A, for replication. Replication occurs when each treatment is applied to more than one experimental unit. This helps to assure that the effect of the treatment is not due to some characteristic of a single experimental unit. It is recommended that each treatment group have the same number of experimental units. And then we're going to collect and process the data by measuring the value of the response variable for each replication. Any difference in the value of the response variable is a result of differences in the level of treatment. And then we're going to test that claim. So this is the subject of inferential statistics, which is what we're doing. Okay? And inferential statistics is the process in which generalizations about a population are made on the basis of results obtained from a sample. Provide a statement regarding the level of confidence in the generalization. Methods of inferential statistics, again, are going to be presented later on as we get further into the course. Okay, and our objective number 3 is to explain the completely randomized design. A completely randomized design is one in which the experimental unit is randomly assigned to a treatment. Okay, so let's take a look at an example now. Okay, so the octane of fuel is the measure of its resistance due to resistance to detonation, with a higher number indicating a higher resistance. An engineer wants to know whether the level of octane in gasoline affects the gas mileage of an automobile. Assist the engineer in designing an experiment. Okay, so for step 1, we want to define the response variable. The response variable is the miles per gallon. And for step 2, we want the factors that affect your miles per gallon. They could be something such as your engine size, your temperature outside, your driving style, the driving conditions, or any other characteristics of the car. Okay, so for step 3, we're going to use 12 cars, all of the same model and year. Again, we're going to try to control some variables by doing that. And here in step 4, we'll talk about that. So we're going to list the variables and their levels. Okay, so octane level, that's going to be manipulated at 3 levels. So we're going to do 3 different treatments. Treatment A is going to be 87 octane. Treatment B is going to be 89 octane. And treatment C is going to be 92 octane. Your engine size, again, that's something that we can control. We're going to fix that. So again, that's one variable we can take out of the equation. Temperature, that's uncontrolled. I have no control over whether the temperature is going to be 75 degrees today or 32 degrees. Okay, but what we will do is we'll make it the same for all 12 cars. Okay, driving styles and conditions, all 12 cars are going to be driven under the same conditions on a closed track. So they're all going to be fixed. Again, how a car performs, say, in the snow, if you're driving in 4-wheel drive, is different than how it is going to perform in the summer, in the middle of the heat, or in some wet roads or dry roads. Other characteristics of the car, all 12 cars are going to be the same model year. However, there is probably variation from car to car. To account for this, we're going to randomly assign the cars to the octane level. So step 5, again, we're going to randomly assign 4 cars to the 87 octane gas, 4 cars to the 89, and 4 cars to the 92. We're going to give each car 3 gallons of gasoline, and we're going to drive the cars till they completely run out of gas, and then we're going to compute the miles per gallon. So we're going to see how far they went. And then we'll determine whether any differences exist in miles per gallon. Okay, so here's kind of a picture of what's going on for that completely randomized design. So we took our 12 cars, we split them into 4 equal groups, and then one group is getting the 87, one group is getting the 89, one group is getting the 92. But in the end, we want to know the same thing. We want to know the miles per gallon for each one of those groups. Okay, matched pairs design. So a matched pairs design is an experimental design in which the experimental units are paired up. The pairs are matched up so that they are somehow related. That is, the same person before and after a treatment, twins, husband and wife, same geographical location, and so on. There are only 2 levels of a treatment in matched pair design. Okay, and the 2 levels are you're either getting the treatment or you're not getting the treatment. Okay, so let's take a look again. We talked about this milk with xylitol example before, so it's going to be that same example again. So xylitol has proven effective in preventing dental cavities when included in food or gum. A total of 75 Peruvian children were given milk with and without xylitol and were asked to evaluate the taste of each. The researchers measured the children's ratings of the 2 types of milk. So for part A, what is the response variable in this rating? Again, the response is whether the kids like it or they don't like it. So that's their rating. For part B, think of some factors in this study which are controlled and which factors are manipulated. So the factors that you can control are whether you're getting the xylitol, you're getting the milk with the xylitol, and the factors that are not controlled are the age and the gender of the children, and the factors that were manipulated are the milk with and without the xylitol. That's the manipulation. What are the treatments and how many are there? Again, your treatment is you're getting the milk with the xylitol or you're getting the milk without the xylitol. How many treatments are there? There's 2. Okay, and again, this is a matched paired design. Again, 2 levels of treatment. You're getting it with or without the xylitol. So your experimental units, they're the people that are going to be drinking the milk. And in this particular example, that was your 75 Peruvian children. And for part F, why would it be a good idea to randomly assign whether the child drinks the milk with xylitol first or second to remove any effect that the order has in which the milk is drunk? If you've ever taken a sip of Pepsi and then for whatever reason, then taken a sip of milk, that milk tastes disgusting after you take a sip of milk, or vice versa. So you kind of want to randomize that so that you make sure that the flavor of one does not affect how you react to the flavor of the other. Do you think it would be a good idea to double blind this experiment? Sure. Hey, obviously you don't want the kids to know which one they're getting because again, that would affect whether they say they like it or they don't like it. And again, if you double blind, then as the researcher, if I'm the researcher, then I can't affect the kid's choice as well. Okay, because something that I can do, whether it's conscious or unconscious, can affect how the kids react to that milk if I know which one is which. Explain the randomized block design. So grouping similar homogeneous experimental units together and then randomizing the experimental units within each group treatment is called blocking. Each group of homogeneous individuals is called a block. Confounding is something that occurs when the effect of 2 factors, explanatory variables, on the response variable cannot be distinguished. A randomized block design is used when the experimental units are divided into homogeneous groups called blocks. Within each block, the experimental units are randomly assigned to treatments. So we're going to go back and look at our English department again, who's trying to do that online versus in-person instruction. So recall the English department is considering adopting an online version of the freshman English course. After some deliberation, the English department thinks that there may be a difference in the performance of men and women in their traditional and online courses. To accommodate any potential differences, they randomly assign half of the 60 men to each of the 2 courses, and then they do the same for the 70 women. When you do it that way, that's called a randomized block design. Okay, the genders are what are going to form your blocks there. This way, gender will not play a role in the value of the response variable or your test score. We do not compare test results across gender. Okay, so what is that going to look like in a picture form? You have your 130 students, 60 of whom are men and women. So you're going to separate it into the men and to the women. Okay, and then again, when you're going to take your men and you're going to split them into online and traditional, and your women into online and traditional, and then you're going to compare the test scores there and the test scores there. You do not take the test scores and compare them here to here. Okay, and that is the end of this section.